Okay, so our next speaker is Jonathan Madajian. Thank you. Madajian, Jonathan Madajian. And he's going to be speaking on simulations of directed energy thrust on rotating asteroids.
So this actually ties in right with what he was just talking about, because what you're working on is detecting asteroids, and we're working on deflecting them. So first I'm going to give you a problem and our solution to it. I'm going to go over our theoretical models, discuss our research results, and then give you some applications. I think a lot about meteors, the purity of them. Boom, the end. Start again. From the recent Avengers movie. Asteroids have been a big part of popular culture and have a lot of money behind them as far as interest, but they're not just fiction. As he mentioned, just 2 years ago, an asteroid exploded over Russia. It didn't even hit the ground. And it injured over 1,000 people and caused roughly $33 million in damages. We would like to prevent this type of problem. And our solution is the D-STAR project. Directed Energy System for Targeting of Asteroids and Exploration. And yes, the R is in the middle of exploration. It's a laser array that we would put in the sky, powered by solar panels, that we could use to deflect asteroids. And our first mission we could pull off for less than $5 million. Now you're thinking, what in the world, how does this work? So the idea is, you have an incoming laser beam on the asteroid, which heats up a laser spot. And then you heat it up to the point where the asteroid starts ejecting mass. So stuff's flying off in one direction. And then that causes the asteroid to go the other direction. And we have lab experiments that prove all of this, but that's another person's project in our lab. So my part is dealing with rotating asteroids. And this is a profile of asteroids that rotate. You'll notice here that there's this sharp 2-hour cutoff when you compare diameter to period. That's the gravitational limit. That means that these up here in the green box are rubble piles that are generally gravitationally bound and that have a period that's independent of diameter and dependent on density. Down here are the super fast rotators. Those are the ones that are molecularly bound, so you can think of them as rocks and ice and things like that. And they have an irregularity in their period due to the York effect. And then everything to the left of this line is, like he said, would be broken up in Earth's atmosphere. Everything here is less interesting as far as a defense standpoint goes, but they do have an interesting point for research purposes. So what I actually do is work on asteroids that rotate. And the fun thing about rotating asteroids is that when you hit it with a laser beam, the spot smears across the surface. And the mass ejection happens at an angle. And the fun part is the thrust vector is no longer in line with your laser beam. So when you hit a rotating asteroid this way, it might fly off that way. So we modeled this using 4 equations. One for the flux of the laser, a Gaussian beam profile, which is fairly standard. To model the radiation off into space, we use Stefan Boltzmann's law. To model the flux of conduction into the asteroid, we used Fourier's law. And then to measure the flux of ejection, we used Antoine's equation and a modified linear equation. Now, if you haven't fallen asleep already, I'm going to dive into the math. So, the flux of the laser is calculated using the beam radius, the standard deviation for the beam, and the laser power. And there's the equation right there, it's Gaussian beam profile. Stefan Boltzmann's law just requires his constant and the temperature K. And there you go, sigma to the 4th. Fourier's law has temperature and thermal conductivity. And the last one is the messy one. This takes an entire slide, so brace yourselves. All right, Antoine's equation takes temperature in degrees Celsius, which is really weird, and you get vapor pressure from that. You use vapor pressure to calculate the mass ejection flux, and then use the mass ejection flux along with the heat of vaporization to get the flux of ejection. So basically, you see the 4 equations on top. You use the flux of the laser is going 4 places: radiation, conduction, and ejection. And this is the messy one that accounts for ejection. Now, I don't feel like solving all that math, so we have a program called Console Multiphysics that solves it for us. It solves the math. It's a multiphysics program, so all of those different components that I showed you are interdependent, so each one affects the other, and this program can handle that. It's a finite element analysis program, which means that it solves all 4 of those equations for each tiny element in this image, and there's probably like 10,000 elements or so. So it basically takes the asteroid, breaks it up, solves the equations for each little piece, and then outputs a temperature in 4D, so 3D plus time. Now I know what we actually care about is our results. Who cares about the math? So this is what Console outputs for us. This is a laser beam incoming to a rotating asteroid, and you're seeing the temperature gradient across the asteroid. So you see as the laser turns on, the asteroid rotates and the heat gets smeared across the surface. So, actual results. Thrust and thermal conductivity. Turns out when we increased thermal conductivity by 250,000%, it only had a negative 2% change in the thrust. So that means is that the green arrows right there basically don't contribute to the overall thrust. So for this next chart, I'm going to define x to be in the direction of the laser beam and y perpendicular to that. So if you look here, this has thrust on the y and period on the x. Over here, this is the stationary case where there's a really large period, so it's basically not rotating. When that happens, the brown, which is the x-coordinate of the thrust vector, approaches the black, which is the maximum thrust. Over here, this is the fun part, and this is why I get so excited about all this. This is when the blue, the y-coordinate, peaks. So that's basically when the asteroid is rotating at just the right speed such that when you hit it, it'll fly off perpendicularly to the way you struck it. And then this last section, this is the super fast rotators. And this is like inhumanly fast. But the fun thing about it is that we discovered something new. If you hit an asteroid that's spinning ridiculously fast with your laser, you'll have a smear that's equal around the entire thing, and it actually won't push it anymore. So, some other applications of this project. Besides defending the planet, you could also use this for detection. You can scan your laser across the sky and try and detect asteroids. If you have the ability to manipulate asteroids, you can also capture them, and in the future, mine them for resources to reach the final frontier. Other applications include composition analysis. You can shoot your space laser at a rock and see what flies off of it and then analyze it with spectroscopy. You can mitigate space debris. So like I said, there's that rocket booster that's just floating around up there. You can push it into a more desirable orbit so it won't hit Earth. Interstellar propulsion. All right, this is a can of worms. But if you have a space laser, you can use the radiation pressure from the light beam to push spacecraft around. And we've proven that you could actually get them up to a quarter the speed of light, which means that you could actually get to the closest star in 17 years and get to Mars in a week. And power beaming. You can send your laser power to power the craft that you're sending, or power a base on the moon, or whatever you feel like. And the best part is, because the way our system is designed, you can do this all simultaneously. And that is the D-STAR project.
Questions?
Yeah.
How much energy do these lasers have to break apart an asteroid or eject any mass?
So, depends on the size of the asteroid, naturally. You typically have to heat the surface up to about 3,000 Kelvin. So we're able to do that in our lab with lasers that are just 40 watts, and that works. Yeah.
So, this laser would be orbiting around us as well, right?
So we have two separate missions. One is the stand-on mission, which means you actually send the craft to the asteroid that you want to deflect. So that's a one-time use mission. And that's a good place to start because it's a small craft and it goes there. The standoff case would orbit Earth and be a much larger laser that could multitask and do all these different things at once.
So no Bruce Willis, huh? Sorry. So this sounds like an extremely important thing to get right. If you get things wrong, you could actually put, if there's a threatening asteroid, you could actually put yourself in a worse situation than you started off with. For example, if you broke it into little bits accidentally.
Right.
Is that a possibility?
Yeah.
Or danger?
So the danger of creating more danger is always something to think about. One case that we've been considering is hourglass-shaped asteroids, which tend to be fairly common. And you have this problem of if you shoot it in the middle, you break it off into two parts, and now you have two problems. And there's a lot of research that's being done into optimizing where you point your laser. And that's a lot of what we're trying to do now, is plan all this stuff out, figure out the physics before we go to space, and oops, it doesn't work.
Well, even worse oops, it made things worse.
Yeah, exactly. Yeah.
So you said you tested this in the lab, right?
Mhm.
Do you have more images?
Do we have what?
Images of
I don't have the graphs with me. I could show you some on our server if you like. But most of that has been comparing the laser power to the thrust induced on the asteroid.
Do you guys, so since you worked with this in the lab, do you also deal with the rotating thing? How did that work?
It totally works. If there was internet, let's see, actually no, I have a video, I can show it to you. Okay, so this is an asteroid rotating in the vacuum chamber, and the laser is incoming on your right. And as you can see, the asteroid slows down and starts spinning the other direction. Let's see, can someone grab the lights? So here's the same thing again. The laser beam's incoming on the upper right. The asteroid slows down and starts rotating the other way. Let's play the video from the beginning. Yeah. There you go. Any other questions?
Okay, let's figure